Let's continue our discussion of logarithms, shall we? And what I'd like to do is to look at a graph of the logarithmic function in which we have y equals log of x, and remember now we are in base 10, so that certainly our graph is going to pass through the point of 1 comma 0, and also notice here at 10 comma 1. All right? Now, I think from what you have done thus far, you have been able to find values of particular values from our tables, isn't that right? But suppose, for example, we were interested in finding the logarithm of a number such as 2.346. And I think you will agree that all of our tables will give us, most of the tables that we have been using, a value of 2.340. Also, we may find 2.350. Is that right? And so now we're faced with the problem of finding a value which is between those two. And the method that we will use is called a linear interpolation method. Now let's take this part of our graph, and what I'd like to do is to enlarge it, so to speak, and let's then look at this picture as we see it right here. Now notice that I've had to distort the curve here so that we can look at this line here, which is then the straight line joining the points A and C. And actually the curve is much, much closer to the actual line segment. Now, here we have the point that I have taken of 2.340, and I've already looked up in our tables the value of that, which is the logarithm of 2.340, which is 0.3692. Similarly, at 2.350, the logarithm of that number is 0.3711. And now here then is some number 2.346, in which we would like to find this point right here, which is on that curve, namely the logarithm of 2.346. All right? Now the approach that we're going to use is to draw that straight line segment and find the value of h at the point C prime. And our assumption is that indeed the point C prime is going to be very close to the value of C, which is on the curve itself. All right? And the method that we can use in order to do this is by linear interpolation based upon what? We have done this once before, and what do you think we would like to do? Well, Peter?
Slope.
Let's look at the slope. Let's look at the slope, say, of AC prime and the slope of AB. And what then will hold true about the slope of those two segments? Peter?
No, they will be equal.
They will be equal. So let's come over here and talk about the slope of the segment AC prime is then going to be equal to the slope of the segment AB. All right? And let's see what we may say about that. Now again, looking at our picture, the slope of AC prime is this height divided by this length. Isn't that right? So it's then going to be h, it's the difference of the y coordinates, minus this number, which is 0.3692, divided by what values? But this length, namely this point of what? 2.346 minus what point? 2.340. Is that right? That's that slope number, and it then must be equal to the slope of the segment AB, and it then is going to be this height divided by this length. And now let's see, this height we may determine by what? We have there 0.3711 minus, and what then is our other height but 0.3692, all divided by the difference in their x coordinates. Is that right? Which is then going to be what? 2.350 minus 2.340. Okay? Well, let's now simplify this somewhat. Our numerator here, we can't do too much with that. Divided by, now here we have 2.346 minus 2.340 is what? 0.006. And that then must be equal to, now the difference between 3711 and 3692 is what? It's 0.019. Is that right? If we were to add 19 to 92, 692, I think we'll end up at 711. Divided by then what? 2.350 minus this number is 0.010. Is that right? All right. Now let's look then at this sentence. Let's decide to multiply both sides through by 1,000. All right. And if we were to do so, the numerator or the denominator here would be simply the number 6, and here the denominator would simply be the number 10. Now let's keep that in mind as we then, let's then also multiply both sides by the number 6, all right, so that I may write this as 6/10. I would rather write this as 6/10 right here, and we have 0.0019. All right, now let's think of this number of 6/10 as now as 0.6 times 0.0019. And let's see now, 6 times 9 is 54, and 11, is this right? Is my arithmetic correct? And now we want to take what? Now it's 1/10 of that, so indeed we need another 0. Am I correct now? Yeah. And our decimal point, I believe, is right here. And notice here we have 5 digits to the right of the decimal point. And since our answer is only good to 4 digits, we may interpret this as what? As simply 0.0011, all right? In which we may think of simply dropping that number 4. Well, let's then add this number to both sides, and if we were to add 0.0011 to this number, we end up at what value? Of 0.3703. Is that right? And therefore, our conclusion is that the logarithm of the number we started with, namely what? 2.346 is approximately equal to what value? But 0.3703. Now, of course, all of our logarithms are approximations, and this linear interpolation then is going to give us quite an accurate value. In fact, within that nearest, for most values of our logarithmic tables, the last digit here is going to be a significant digit. That is, it will be accurate to the nearest 10,000. All right? Well, there's no need for us to have to go through this slope process every time we want to interpolate. And I think very quickly you would like to say that let's find a more efficient method of doing so. And what I'd like to do now is to look at a more efficient method, in which I've set up a little table here, in which here we have some value of x, 2.340. We can read that number in the table, which we have just done. We know that the number that we are concerned with is going to be between these two, namely 2.346. And now the question is, what number do we want to insert in here? Now, notice the easy way in which one can do this, and simply take this as a ratio, using the idea of the slope numbers as we just have. Let's look at this difference. The difference between these two numbers is 6, and then, now this is 6/10,000ths understood, and then the difference between these two numbers is what? 10. So 6 is to 10 as, now the difference between these two numbers, whatever it happens to be, let's call it C, as C is to the difference between these two numbers. And the difference between those two numbers to the nearest, to the 10,000th is what? 19. And notice now you have a very simple little ratio. 10C then is equal to 6 times 19, which is what number? That was what? 114, is that right? 114. C then is equal to 11.4. And since we are talking about this as the 11.4 10,000th, so to speak, we're going to do what with the number 11? What would you like to do with the number 11? But to, Bill?
You add that to the 0.369.
All right, we will add it to this number here, and when we do so, we have what? 0.3703, and I think you will agree that that's the number that we got from the previous method. So here we have the logarithm of 2.346 is equal to 0.3703, and indeed that's our answer. All right? Well, let's utilize the same method as we go in reverse. That is, let's find the anti-logarithm of some number. And here I picked out some other value, 2.5396. Now notice here is our characteristic and our mantissa. So if you would then have to find the antilog of this number, you're looking inside the table for 5396. And you don't see that number, but you do see 5391, and you also see 5403. So the number that you want is going to be between those two, namely 5396. Is that right? Now let's do exactly the same process, in which the difference between these two numbers is what? 5 is to this difference, which is between 391 and 403 is 12. 5 is to 12. As this difference, let's give it some name, call it D, is to this difference. And this difference, of course, is what? As D is to, since we are thinking of it in terms of 10 thousandths, let's call this D is to 10. Is that right? So we then will have what? 12D then is equal to what? Is equal to 50. And then D is equal to what number? But this is about 4.1 approximately. Is that right? Let's say that it's 4.1, and since our numeral is simply good for that fourth digit, therefore the anti-log is going to be equal to what number? And Bill?
346.4.
346.4 then will be that significant digit, okay? So therefore the anti-log of this number is then going to be equal to 346.4, and notice then that we have extended our tables and in order to be able to go from 3 digits in order to read the fourth digit. All right? And it's by this method of linear interpolation that will enable you to do so. So let me give you your homework assignment in which I'd like you to practice some of these problems.